Hi, students. Sorry, I'm in the middle of a game here. I'm playing Untangle. And the way that this game works is I just have to make sure that the lines don't overlap. All right, so I just need to move these dots around, these vertices around to make it so then they don't have any edges that cross. Hmm, let's see. Where could I put there we go. Oh, this one looks a little bit harder. Where could I move this? Move this one. Oh, all right. I think maybe you get the idea here. What I'm playing right now is an actual computer game. If you go to this website right here, you could play it as well, as long as you're not at school because it's blocked and I couldn't get it unblocked. But the reason why I was playing that game to start off was because this is actually one of the concepts that we're going to talk about today. All right, what I was doing there, untangling the graph, I was just determining whether a graph is planar or not. All right, so here's the definition of a planar graph. It's a graph that can be drawn so that no two edges intersect except at a vertex. All right, so what I was doing was I was moving those vertices around and I was making it so edges did not intersect. And that is what it means to be a planar graph. All right, so I wasn't changing what the graph looked like at all. I mean, I kind of was changing how you saw it, but I wasn't changing anything about the graph because it still had the same number of vertices, it still had the same number of edges, and the edges or the vertices that were adjacent to each other was still adjacent to each other. All right, so a few things to know about a planar graph is that every planar graph has a chromatic number that is less than or equal to 4. Right, so thinking back to last class when we learned about the four color theorem, all right, that applies to planar graphs. All right, the bad news is if a graph is not planar, we don't know anything about how many colors it will take to color. It might take more than 4, but it also could take 4 or less. All right, so the only thing that we know is that if a graph is planar, it has to have a chromatic number of 4 or less. If the graph isn't planar, the chromatic number could be anything. All right, so here I have some graphs, and we're going to try to determine whether or not the graphs are planar. All right, and so ways to determine whether the graphs are planar. Honestly, the way that we're going to do in this class is just try to untangle them. All right, try your best. Keep the vertices, okay? Keep the certain vertices adjacent to each other. All right, but then just try to redraw their edges. And remember that edges, okay, the way that you work with lines, you usually consider lines to be straight. Okay, edges don't have to be lines. They can be curved. All right, so try to just redraw the graphs to make it so their edges don't intersect at all. Before you start just untangling, however, I would double check what the chromatic number is. All right, because if it happens to be more than 4, don't try to untangle because if it's more than 4, the graph cannot be planar. However, if it's 4 or less, then you're going to have to play around with it because it might be planar, it might not be. All right, once the graphs get to be so large, it's going to be hard to just play around and determine whether or not the graph is planar just by trying to untangle. So really what mathematicians do is they look to see if there are what are called K33 or K5 subgraphs. And that probably does not mean much to you right now. Maybe K5 does. Okay, that should ring a bell from last time. That means a complete graph with 5 vertices. All right, if that can be found within the graph, it means that your graph is not going to be planar. And this right here, same thing. But again, that doesn't mean much to you right now. We're going to discuss that here in a little bit. So I'm going to go back up here to these graphs. And first I'm going to check the chromatic number. And then if it is 4 or less, then I am going to try to untangle the graph. All right. So quick review for how to find the chromatic number. Pick a vertex, doesn't matter which one. Try to start off with the one that has the highest degree. All right, I'm going to pick this vertex. I'm going to color it a color. It's adjacent to all of the other vertices, so nothing else can get the same color. And then I'm going to get another color, and I'm going to color another vertex, the next one of highest degree, but these are all tied with their degree of 3. All right, so then I'm going to get a new color because this vertex was adjacent to all the other vertices that were left uncolored. So I'm going to get a new color. I can't color this one because it's adjacent to this one, so I need another color. All right, so that means I colored this graph using 4 colors, which means the chromatic number is 4. That means that this graph could be planar. It might not be planar. I am just going to have to play around with it. All right, so hopefully you can see on this one, it's not that hard of a graph to untangle. If I were to just take one of these diagonals, it doesn't matter which one. All right, so this is going to be kind of tricky here, but I'm going to do this. I'm saying erase this. I can't really erase it right now, but pretend like this vertex right here connecting this red to this light blue vertex. Okay, pretend like this edge is not there. Okay, pretend like we're removing it, and instead draw it on the outside. All right, there we go. Now we have made it so the graph is planar. Another thing to note about this graph, okay, quick review from last time, it had 4 vertices. It is a complete graph, all right, because I can go from, or if I look at each of the degrees of each vertex, it was degree 3, degree 3. This vertex was adjacent to the other 3 vertices. This vertex was adjacent to the other 3, and so on. All right, next graph, same thing. I'm going to first start off with the chromatic number, and then there I will try to untangle if necessary. All right, so looking at the vertex of most degree, and it looks like they are all the same. They're all degree 4. All right, so that means I'm going to color this first vertex with the first color. All right, instead of actually coloring now, I'm just going to put numbers by them. So I'm going to say that this is the first color. But it is adjacent to all the other vertices, so nothing else can get the same color. So then I'm going to go and give this vertex color 2. But it's adjacent to all the other ones. And so then I need a third color for this vertex, but it's adjacent to the remaining 2. So then I need a fourth color, but it's adjacent to the remaining 1. So then I need a fifth color. All right, so what that means is the chromatic number for this graph is 5. All right, and so this tells me something. This tells me because the chromatic number is 5, this graph cannot be planar. I can't try to untangle this. It won't work. All right, I can get some of the edges untangled, but I can't get them all untangled. Why do I know that? Well, one reason is because the chromatic number was 5, and if the graph is planar, the chromatic number has to be 4 or less. All right, this is actually a complete graph with 5 vertices. It was a complete graph with 5 vertices because the degree of each vertex was 4 because it was adjacent to the remaining 4 vertices. All right, for my next graph, I'm going to do the same thing. I'm going to try to color it first and then try to untangle if necessary. So it looks like this vertex is degree 3. So I'm going to start off with it. I'm going to give it the first color. And then it is adjacent to this one, and this one, and this one. So then I can give this vertex, the one that it's not adjacent to, the same color. All right, and then I'm going to move on to another vertex. I'll choose this one. I'm going to give it the second color. It's not adjacent to this one, so this one can receive the same color. And this one's not adjacent to either of those, so it can also receive the same color. So this graph has a chromatic number of 2. All right, so chromatic number of 2, unfortunately, doesn't tell me anything about the graph being planar or not. It could be, it might not be, we don't know. So we're just going to have to try to untangle the graph. So what I'm going to do is I'm going to try to make my 5 vertices, and I don't have to keep them where they are. I'm going to see if I can. All right, I'm going to try to, sorry, that's a vertex. It's just really bad. Same with this one. I'm going to try to keep the vertices where they are and then just redraw their edges. So let's see. This one was adjacent to this one. This one was adjacent to here. And there's no unique way we could do this differently. Let's see. So then now I need to get this vertex adjacent to this one. But if I go here, it's going to cross. So I'm going to go around. All right, and then I need this vertex adjacent to this one. All right, so what I could do is go right through here. All right, and let me double check. I have 1, 2, 3, 4, 5, 6 edges. I have 1, 2, 3, 4, 5. Oh, and that one is the 6th one. Okay, so I have everything. I was able to untangle my graph, and so that means that this graph is planar, and it happens to have a chromatic number of 2. All right, to speed things up a little bit on this next graph, I went ahead and colored it. So I started off with the vertex of highest degree, colored it with the first color, and I wound up finding that this graph has a chromatic number of 3. So while that's an important piece of information when it comes to planarity, having a chromatic number of 3 doesn't tell me if the graph is planar or not. So what I'm going to have to do instead is just try to untangle it. All right, so I'm in the process of trying to untangle my graph, and this is what I have so far. I have all of these top vertices with their edges. I have this vertex right here, which is this one, and I have it adjacent to the ones that it needs to be adjacent to, and now I'm working on this vertex right here. So it needs to be adjacent to this one, so it needs to be adjacent to this one. So what I'm going to do is I'm going to come up, and I'm going to come around here. All right, and then it also needs to be adjacent to this one. That's no big deal. And then it needs to be adjacent to this one down here. I can do that. All right, so now I'm going to try to get this vertex to be adjacent to the ones that it needs to be. So I'll make it adjacent to this one, and then I try to get it to this one, and notice this is trapped. All right, I could try to rework this, but try as much as you'd like, and you're going to find that this graph is never going to be able to be untangled, so this graph is not planar. All right, and that's really what we're going to be doing, all that we were going to be doing in our class with planarity and not, is just trying to determine whether we can untangle the graphs, and then also knowing that all planar graphs have a chromatic number of 4 or less. Next, we're going to talk about what are called bipartite graphs. Okay, bipartite graphs, and you're probably already thinking, okay, it has the prefix bi, which it means 2, so it probably has something to do with 2, and that is exactly right. A bipartite graph is going to be bipartite if its vertices can be divided or split into 2 distinct sets, so that each edge of the graph has one vertex in each set. All right. Something else to note about bipartite graphs is because they can be divided into 2 distinct sets, okay, and each vertex that's in one set is non-adjacent to each other, okay, and then each vertex in the other set is also non-adjacent to each other. It means that the chromatic number will always be 2 for bipartite graphs. There are special bipartite graphs, and that's going to be a bipartite graph where when you have a vertex in one set, it's adjacent to all of the vertices in the other set, and vice versa. All right, that is going to be a complete bipartite graph. And just like our regular complete graphs are denoted with a capital K with a subscript, same with a bipartite graph, except it has 2 subscripts, and the first subscript represents how many vertices are in the first set, and the second subscript represents how many vertices are in the second set. All right, so I'll show you some examples here in a little bit for that. But what we're going to do first is we're going to look at this graph right here, and we're trying to determine if it's bipartite, and we're going to come up with an algorithm, so a method for us to determine if it's a bipartite graph or not. Okay, so the first thing I'm going to do, bipartite graph, I'm going to go ahead and make 2 lists. One is set 1, and the other list will be called set 2. And I'm going to start with any vertex on my graph, and I'm going to put it into set 1. All right, so why not start off with A? So I'm going to take vertex A and place it into set 1. All right, here's what I'm going to do next. I'm now going to list any vertex that is adjacent to A in set 2. So A is adjacent to D, A is adjacent to E, and A is adjacent to F. So now what I'm going to do is I'm going to use vertex D, then E, then F, and I'm going to list any vertex that they are adjacent to in set 1. So D is adjacent to A, but that's already in set 1, so I'm not going to put it twice. D is adjacent to B. D is adjacent to C. All right, E is adjacent to A. E is adjacent to B. E is adjacent to C. F is adjacent to A, F is adjacent to B, F is adjacent to C. All right, so now I need to double check B. Is there any other vertex that B is adjacent to? B is adjacent to only D, E, and F, which good. Those are just in set 2. C is adjacent to D, E, and F, which again, those are just in set 2. All right, so I didn't have any vertex that was both in set 1 and in set 2. All right, which means that this graph is bipartite. All right, because this graph was bipartite, we could label it as a K. Well, it's going to be a complete bipartite because when we were going through, vertex A was adjacent to all of the other vertices in set 2. Vertex B was adjacent to all of the other vertices in 2, same with C, and then D was adjacent to everything in A, E was adjacent to everything in this first set, and same with F. So it was a complete bipartite graph, so we're going to use K to represent it. All right, and then we're going to use subscripts to say how many vertices are in each of the sets. So set 1 had 3 vertices in it, and set 2 had 3 vertices in it. So we could represent our graph as a K3 graph. Okay, let's go ahead and do another example, one that probably doesn't look as much like the last graph was as 2 separate sides. So that one looked like a bipartite graph. This one doesn't necessarily. So let's see if it's going to be one. All right, so I'm going to start off with any vertex. It doesn't matter which one. So I'll start off with A, and I'm going to put it into the first set. And then what vertex is A adjacent to? It's adjacent to B, D, and F. So I'm going to put B and D and F into set 2. All right, and then I'm going to go to B. All right, so B is going to be the one that I do next. B is adjacent to A. I already have that listed. B is adjacent to C. So I'm going to put C into set 1. All right, D, I'll go ahead and do that one next. D was adjacent to A. D is adjacent to C. And D is adjacent to E. So I'll also put E into set 1. All right, F. F is adjacent to A. F is adjacent to C, F is adjacent to E, and F is adjacent to G. All right, so now I took care of every vertex that B, D, and F were adjacent to, and so far no issues. And so then I already looked at A, now I need to go to vertex C. And I need to make sure that those vertices are in set 2 that C is adjacent to. So C is adjacent to B. There it is. C is adjacent to D. There it is. C is adjacent to F. There that one is. All right. And then I'm going to go to vertex E. All right. So next up is E for me to double check. So E is adjacent to D, which is in set 2. E is adjacent to F, which is in set 2 already. E is adjacent to G, which is not in set 2 already. So I need to put G into set 2. And now notice I just had vertex G that I placed in set 2, but I already had it in set 1, which means that this graph is not bipartite. Because E and G are in set 1, they cannot be adjacent to each other, but right here there's an edge connecting them, which means that this graph is not bipartite. All right, another vocab word, today is a lot of vocab, is going to be graph complement. All right, so it's not saying, hey, that's some really good looking vertices you have there. No, graph complements aren't that. A graph complement means that you have the same number of vertices. You still have the same vertices, okay, but it's going to include every edge that was not in the other graph. Every edge that was in the other graph will not be included in the graph complement. All right, and the way that we're going to denote it is by, if we name this graph with a capital letter, this graph is going to be using the same capital letter, but then we're going to use this bar on top. So this is actually called G. This would be graph G, and this would be called graph G naught. All right, graph G naught, because it's basically saying this is going to be everything that this one wasn't. except the only thing that they have in common are still the vertices. All right, so that's what I've done so far, is here we have a graph. I've already drawn in those vertices, and then now what I'm going to do is I'm going to draw in every vertex, okay, that did not exist over here. All right, so what that means is this vertex was adjacent to these two vertices. So there was an edge here, there was an edge here. This time I'm not going to draw those. Instead, what I'm going to do is I'm going to make an edge to every vertex that this one wasn't adjacent to before. All right, so that means that this vertex wasn't adjacent to this one or this one. So that means I'm going to draw in a vertex here, or an edge there, sorry, and an edge here. All right, for this vertex, it wasn't adjacent to this one. So that means I'm going to now over here in the complement, whoops, oh well, I'm going to draw in an edge connecting those two. This one was adjacent to these two, so it's going to be adjacent now to this one. It already is, and this one. And then this one, I think we have everything now. All right, so that means this would be this graph's complement. Now, that's really all we're going to do with that graph complement. Let's just talk a little bit about some review topics here. This graph is planar because I was just able to draw it with the edges, so it wasn't overlapping. This graph, however, is not a connected graph, all right, because there's no way to go from this vertex now over to this set of vertices. All right, so this graph is not connected. I could also determine the chromatic number of this one. Let's see if I make this one a 1. Obviously, I can make this one a 2. I could make this one also a 1. I could make this one a 2 and this one. This one would have a chromatic number of 3. All right, the last topic that we're going to do today is called a subgraph. So that prefix sub, it means a graph within another graph. All right, so here we have an original graph, and what we're going to do is we're going to determine if this graph can be found in this one. So don't go by looks, all right? This one looks very clearly like a regular pentagon, and nowhere in here do I see a regular pentagon. All right, don't go by looks, go by does this graph contain these vertices? Does it also contain these edges? All right, now it might contain excess, all right, but all of the components to this graph, so each vertex and each edge needs to be contained. It needs to be within this graph up here. So first thing I'm going to do is check vertices. So A, B, C, D, and E. So A, B, D, C, and E. So yes. Now I'm going to check edges. So A to B, right there. There is an edge connecting A to B. So that one's good. B to C, there is an edge. So that one's good. D to C, I found it right there. Is there an edge connecting D and E? D and E, yes there is. And A and E. A and E, no, there is not. So this one, A and E, that edge does not exist in this graph up here, which means that no, this graph is not a subgraph of this one up here. All right, so now let's do the same thing for this next one. Again, don't go by looks, go by vertices and edges. So A, B, C, D, E, and F. Yes, this one also has F up here. So we already know that A and B existed because of this graph over here. B and C, again, we know that one. We know C and D. We know D and E. But let's look at E and F. All right, so E is adjacent to F, so that one exists. A and F, yes, there's an edge connecting A to F. So because we were able to find all of this graph, all of its vertices and all of its edges within this graph, it means that yes, this graph right here is a subgraph of this one. All right, so there was a lot of new vocab there. We didn't really have anything too intricate, just a lot of new vocab to add in. That's probably the hard part, is keeping track of what certain things mean and starting to develop some algorithms for how to do certain things. So that's going to be the tricky part with this unit, is knowing all of your vocab and then also remembering how do I do each of these tests. All right, one more thing to consider before I leave you on this video is planarity in real life. I've had the privilege, maybe, I don't know if that's the right word, of working with some electricity, doing some home remodeling. But if you become an electrical engineer, or if you know anybody that is an electrician, planarity is an important concept in real life because you do not want to get your wires crossed. All right, you might be able to get some electricity running through it with some wires crossed, but that's never good because it is possible that you could have the circuit short out. All right, so planarity in real life, not sure about how much we can apply the other parts to real life. All right, but planarity in real life in the electronics industry, it is an important one.